Interchangeability. What do we mean by the term interchangeability? In engineering, every component is required to fit or match with some other component. Let's say a M6 nut. A M6 nut is required to fit a M6 bolt. Similarly, if we take the example of a cylinder head and engine block, the cylinder head is required to fit the engine block and perform the intended function. The assembly should perform the intended function smoothly without any excessive noise or leakage. So how do we ensure that M6 nut will perfectly match a M6 bolt? In fact, every day, millions of M6 nuts and bolts are manufactured. And if we randomly pick a M6 nut and fit it on a M6 bolt, it will fit smoothly. And similar is the case for engine block and cylinder head. Thousands of engine blocks and cylinder heads are manufactured every day. And if we pick a cylinder head of a specific make and fit it on the engine block, it is going to fit properly and perform the intended function smoothly. So how do we ensure this interchangeability? In fact, component parts cannot be manufactured to exact dimensions. There will always be some degree of variability between the parts manufactured. Let's take the case of the distance between flats of a bolt. If D is the distance across flats of a M6 bolt, and if the design size for this dimension D is 10 mm, and if we randomly pick 3 bolts and measure the distance across their flats, it will come out say 10.05, 9.96, and 9.98. So it will not be, all the 3 bolts will not have the same distance across the flats. But as long as our fabricated or manufactured component is doing its intended function properly and smoothly, these slight deviations from the design size are acceptable. In fact, engineering components are manufactured with an allowable margin. So if we take the example of cylinder head and we measure different dimensions of 10 different cylinder heads of the same make, we will notice that there will be slight variations in the dimensions. But these variation will lie within a allowable margin. And as long as the cylinder heads are manufactured within that allowable margin, they will perform the intended function smoothly and properly. To ensure interchangeability, various dimensions of a component should lie between 2 acceptable limits. And the limits of size depend on application. The closer the limit of size, higher will be the manufacturing cost. Now, based on the concept of interchangeability, the limit system and tolerances were introduced. Basic size. Basic size is the size as determined from design calculation. Let's say we design a 32 mm shaft to transmit a specific maximum torque and rated power. So 32 mm here will be the basic or nominal size. Similarly, a 32 mm journal bearing will be designed to support the 32 mm shaft. For this journal bearing, 32 mm will be the design size. But as we know that we cannot manufacture the components to exact dimensions, there will be a allowable margin for this 32 mm journal bearing as well as for the 32 mm shaft. So there is a upper limit of size as highlighted by the arrow B. So upper limit of size is the maximum permissible size for a hole, in this case a bearing. So this upper limit of size is the maximum permissible size. If the size of the bearing is greater than the upper limit of size, then it will not perform the intended function smoothly. It will not support the shaft smoothly and it will produce lots of noise and wobbling of the shaft. Similarly, lower limit of size is the minimum permissible size of the specific component as highlighted by C here. Upper deviation. Upper deviation as highlighted by D is the difference between the upper limit of size and nominal size. And the upper deviation can be positive or negative depending upon whether the upper limit of size is greater than the basic size or less than the basic size. Similarly, lower deviation is the difference between lower limit of size and nominal size. It can also be positive or negative. Tolerance is the difference between upper deviation and lower deviation. The similar terminology is used for the shafts also. And we can see here the upper deviation D as well as the lower deviation E for the shafts shown in this figure is negative. Then there is fundamental deviation. It is the deviation nearest to the nominal size. So in the case of the hole, we can see E is the fundamental deviation, E the lower deviation is the fundamental deviation and it is positive. Similarly for the shaft, D the upper deviation is the fundamental deviation and it is negative. So in the both cases we can notice that the fundamental deviation is the deviation nearest to the nominal size. Little more on fundamental deviation. Lower deviation is also known as E cot inferior. It is represented by uppercase EI for a hole and lowercase EI for a shaft. Similarly, upper deviation is also known as E cot superior, and it is designated as ES, uppercase ES for a hole and lowercase ES for a shaft. And for shaft, the lower deviation is equal to upper deviation minus the tolerance grade. And the similar relation is applicable for the hole also. So let's take the example of the figure A that is representing a shaft. For the shaft A, upper deviation ES as shown in the figure will be the fundamental deviation as it is the deviation nearer to the basic size. And the upper limit of size, that is the maximum size of the shaft, is smaller than the basic size. So the shaft in this case is designed such a way that it will always be smaller than the basic size. Similarly, in figure B, we can see that the lower deviation is the fundamental deviation as it is nearer to the basic size, and the shaft B is intentionally designed in such a way that it will always be bigger than the basic or design size. So the actual shaft might be bigger than the basic size or smaller than the basic size depending on our design requirements. Similarly, for the figure C, the whole lower deviation is the fundamental deviation as shown by the capital EI. And if we look at the figure D, the lower deviation is in this case is 0. So the fundamental deviation in this case is 0. So based on our design requirement, the fundamental deviation can be positive, negative, or 0. But the tolerance grade is the difference between upper deviation and the lower deviation will always be positive. So how do we represent tolerances? So this is a drawing of a component, and in this case we can see different methods of showing the tolerances. For the highlighted dimension, we can see 80 is the basic size and plus 0.1 is the lower deviation and plus 0.4 is the upper deviation. And the lower deviation in this case will be the fundamental deviation. Similarly, here we can see 20G6 is another way of representing the tolerances. According to ISO code system, shafts will be designated as 30 small e8 or 50 lowercase g6. Similarly, The holes are represented as 40 upper D, 9, 25 uppercase at 6. So one thing we notice is for the shaft we will use lowercase letters, and for the hole we will use uppercase alphabets. So as per the ISO coding system. Now this 20G6 is conveying three things. One is basic size, fundamental deviation, which might be the lower or upper deviation, which is whichever is nearer to the basic size, and the tolerance grade. So let's take the example of 30E8 shaft. 30 in this case is the basic size of the shaft. E will be the fundamental deviation. The alphabet small case e will represent the fundamental deviation, and the 8 in the end is giving the tolerance grade. Now we can read what these mean from tables. We'll go to it later. Similarly, for a hole, we are using the uppercase H for this 25H6. 25 will be the basic size of the hole, H will be the fundamental deviation, and 6 will represent the tolerance grade. So according to ISO system, we have this chart to locate the fundamental deviation. In fact, this is taken from ISO 286-1 2010E. So this is for hole or internal feature. As we can see, the alphabets here are uppercase. So in this figure, we can see the blue line is representing the basic size. After that, if we take the example of hole with fundamental deviation B, we can see that B is the lower deviation, and the tolerance will extend upwards from the fundamental deviation, that is lower deviation for the whole B. Let's take example of 40D9 hole. So in this case, 40 will be the basic size, and D is the fundamental deviation. So looking in the chart, we can see that D is representing the lower deviation for the hole, which means that for this 40D hole, lower deviation will be the fundamental deviation, and the tolerance zone will extend upwards from the fundamental deviation as designated by this number 9. So this 40D9 can be represented by this figure. Here we can see that the lower deviation is the fundamental deviation, and the tolerance zone is extending upwards from the fundamental deviation. And once we know the lower deviation and the tolerance, we can find the upper deviation using the formula as shown. So from this figure, we can see for A to H holes, lower deviation is the fundamental deviation. And one more thing that we notice here is, as we are moving from hole A to hole H, the lower deviation is becoming less and less until at H, the lower deviation becomes equal to 0. So for hole A to H, lower deviation is the fundamental deviation, and the tolerance zone will extend upwards from the lower deviation. Now let's take example of 25H6 hole. So here we can see that the lower deviation will be 0. So the lower deviation will be 0. So this hole can be represented by this figure. In this, we can see that the basic size and the minimum limits of size will be same as fundamental deviation is 0. From J to ZC, the fundamental deviation will be upper deviation, and it will be negative. And the tolerance zone will extend downwards from the fundamental deviation. So let's take example of 60P5 hole. So in this case, the P is representing the fundamental deviation, that is negative, and the fundamental deviation is negative, and it is the upper deviation, and the tolerance zone will extend downwards from the fundamental deviation. So the hole for the P will be represented by the figure shown. Here we can see that the upper deviation is negative and the tolerance zone is extending downwards from the upper deviation. So for J to ZC, upper deviation is the fundamental deviation and the tolerances are extending downwards from the fundamental deviation. And for JS, the upper and lower deviations are equidistant from the basic size, and the upper deviation will be equal to half of the tolerance grade and lower deviation will be equal to negative of half of the tolerance grade. Similarly, for the shaft or external feature, the fundamental deviation is determined from this figure. Here we can see for a shaft designated by lowercase b, the upper deviation is the fundamental deviation and the tolerance zone will extend downwards from the fundamental deviations. And we can notice that for the shaft designated with fundamental deviation as A to H, the upper deviation will be the fundamental deviation, and as we are moving from shaft A to shaft H, the fundamental deviation is becoming less and less until at H it becomes 0. And from shaft J to ZC, lower deviation will be the fundamental deviation and it will be positive. The tolerance zone will extend upwards from the lower deviation. So for shaft J to ZC, lower deviation is the fundamental deviation. And once we know the fundamental deviation and the tolerance grade, the other deviation can be found using the formula shown here. Let's take example of 30E8 shaft. So here we can see that E for the shaft designated with E, the upper deviation will be the fundamental deviation and it will be negative. And the tolerance zone will extend downwards from the fundamental deviation. So the shaft E 30E8 can be represented by this figure. Here we can see that the fundamental upper deviation is the fundamental deviation and it is negative. And the tolerance zone is extending downwards from the fundamental deviation. Similarly, for the shaft 30JS, as we have previously discussed, for JS, the upper and the lower deviations are equidistant from the basic size. So in this case, the upper deviation will be equal to half of the tolerance and lower deviation will be equal to minus of the upper deviation.